Welcome back to the deep dive. Today we are shifting gears a little bit. Usually, we take a stack of articles, we analyze them, and we give you the highlights. But looking at the sheer density of the material on my desk today, I mean, it's heavy.
It's literally heavy, yeah. These are not light reads.
We need a different approach. We need to
Right.
sort of change the frame for this.
I agree. It's way too dense for just a casual chat.
Mm,
We're looking at documents from Murata and Renesas that are, they're essentially the blueprints for the next decade of automotive engineering.
right.
These are not product brochures. They're foundational strategy documents.
Exactly. So I want you to imagine we're not just recording a show.
Okay.
Imagine we are sitting in a glass-walled conference room, maybe in Detroit or Stuttgart or, high-rise in Tokyo. I'm stepping into the role of the project lead.
Right.
I'm the one who's on the hook for the P&L, the deadline, and making sure this next-gen EV platform actually, works without bankrupting the company.
And that puts me across the table from you. I'll take the role of the senior technical strategy consultant. You've brought me in to look at the architecture from, let's say, 10,000 feet.
A high level.
A very rigorous, top-down, MECE style analysis to make sure you're not just building a legacy car with a battery strapped to it.
That is exactly the fear. That is the fear that keeps me up at night. We're tackling the e-architecture revolution. And for the elite engineers and technical directors listening to this, I want you to consider this your confidential technical strategy report. We're going to break down how the car's physically changing to accommodate the software dream.
And the source material is fascinating because it represents a convergence. Usually in this industry, you look at power electronics and computing separately from passive components.
Right, they're in different silos.
Completely different style. You have the silicon guys and you have the ceramic guys, and they rarely talk until something breaks. But the intelligence we have today, these deep technical vaults from Murata on passives and sensors, combined with the high-level compute strategy from Renesas, it tells us that you just can't separate them anymore.
It's a package deal.
It has to be.
You can't have the brain without the nervous system.
Precisely. If we apply a mutually exclusive, collectively exhaustive approach to this, the core problem is crystal clear. The industry goal is the software-defined vehicle, the SDV.
Of course.
Everyone wants a Tesla valuation. Everyone wants the subscription revenue, the seamless updates. But the constraints, the things preventing that, are purely physical.
It's not a software problem.
It's not. It's a battle against heat, space, and power density.
So our mission today is to brief the listener, our chief engineer, on how to win that battle. We're not just talking about swapping out a chip. We are talking about a complete teardown of how a car is wired.
Let's open the macro strategy chapter of this report then. We need to define the battlefield before we choose the weapons.
Right.
Okay, let's start with the evolution. For the last, 30, 40 years, we've been building cars on what we call a distributed architecture.
Which, to be perfectly honest, was a necessary evil that just grew into a logistical nightmare.
It was absolute chaos.
Yeah.
The logic was simple, right? I want power windows. Okay, buy a box that controls windows, shove it in the door, run a wire to the battery, run a wire to the switch. I want a sunroof. Okay, buy a sunroof box, run more wires. I want heated seats.
Yep.
Another box, more wires.
And you just repeat that over and over.
For 50 years.
And you compound that complexity, and you end up with a vehicle that has over 100 separate electronic control units, ECUs, just hidden in every single crevice of the chassis.
And the wiring harness. I've seen the schematics for modern luxury SUVs. It looks like the nervous system of a blue whale.
Yeah.
It's massive.
It is the third heaviest component in a traditional car,
The third.
right behind the engine and the chassis. It's incredibly expensive to make because it's hard to automate. Robots really struggle with floppy cables. I can imagine.
And it is a complete nightmare to debug. If one wire pinches in the A-pillar during assembly, good luck finding it. You practically have to scrap the whole chassis.
So the industry realized this wasn't sustainable. We moved to domain architecture.
Right.
And that's where a lot of our listeners probably are right now in their current production cycles. You group things by function.
So you have a body domain controller, an infotainment domain, an ADAS domain.
Exactly.
And it was a step in the right direction. It consolidated some of the computing power. Instead of 100 dumb boxes, you have maybe, 10 or 15 smarter ones.
But
And this is the critical strategic flaw domain architecture groups,
Okay.
things logically, not physically.
Okay, explain that distinction, because that feels like the pivot point for this entire conversation.
It is. So in a domain architecture, you have a body controller. It controls the lights, all the lights. The headlights way up in the front and the taillights way in the back.
Right.
That means you are still running long copper wires from that controller, let's say it's under the dashboard, all the way to the four corners of the car.
So you haven't actually solved the wiring problem.
You haven't. You've just moved the switch. You still have this massive web of copper traversing the entire vehicle.
Which brings us to the target state, the holy grail for 2030, zonal architecture.
This is the inevitable shift. In zonal architecture, we just stop organizing by function. We don't care if it's a light or a motor or a sensor. We organize by location.
Physical zone?
Physical zones, front, left, front, right, rear, roof, whatever makes sense.
So if I'm the front left zone controller, the ZCU, I'm the king of my corner.
You own it. The headlight is yours. The tire pressure sensor is yours. The cooling fan is yours. The window motor is yours. It does not matter what they do. It only matters where they are.
And that changes the ZCU into an aggregator.
That's the term. It acts as a local hub. It gathers all the sensor data. It powers all the local actuators. It digitizes everything right there locally. And then it sends a single high-speed Ethernet stream up to the central compute, the brain.
Wow. That must cut the wiring harness massively.
The studies I've seen suggest a 30 to 50% reduction in harness weight.
30 to 50%.
And that is a direct range extension for an EV. Less copper means less weight, which means more miles per kilowatt hour. It's a direct efficiency gain.
But there's a bigger reason than weight, isn't there? It comes back to the software.
It absolutely does. You cannot have a true software-defined vehicle with a distributed mess. If you want to do an over-the-air update, an OTA, to change how the braking feels or how the lights animate,
Yeah.
you cannot be coordinating that across 100 different microcontrollers from 50 different suppliers, all speaking different dialects of CAN bus.
It's like trying to update a computer network where every computer is running a different operating system from a different decade.
That's a perfect analogy. With zonal, you update the central brain. The central brain sends a command to the zone, turn on the light.
Yeah.
The zone executes.
Yeah.
The zone doesn't need to know why, it just handles the I/O.
It abstracts the hardware from the software.
It's that critical abstraction layer.
Okay, now, putting my project lead hat on, I hear architecture change and I hear risk and cost. Is this actually happening, or is this just PowerPoint engineering?
Oh, it's happening, and the money is already moving. The market quantification data from Renesas and Murata is unequivocal.
Yeah.
Let's look at the business case.
Okay, hit me with the numbers.
The market for zone controllers, the ZCUs themselves, is predicted to grow at a compound annual growth rate, a CAGR, of 23.2% between 2027 and 2032.
23%. In the automotive hardware world, flat is usually considered a win, 5% is a boom, 23 is a gold rush.
It's explosive. By 2032, the volume is projected to reach 1.72 billion units globally.
Billion.
Billion would be because remember, every car needs multiple zones, usually 4 to 6 per vehicle.
Right.
And if we look at just the power management market for the high-performance computing, the central brains, that sector alone is projected to exceed $800 million by 2032.
So if I'm a young engineer listening to this, or a director planning my hiring strategy, if I'm focusing on legacy distributed ECUs, I'm basically painting myself into a corner.
You're refining the typewriter in the age of the laptop.
Yeah.
The R&D budget, the innovation, the supply chain focus, it's all flowing into zones and central compute. Adaptation is, it's not optional.
Okay, we've established the why. We're moving to zones. Now I want to zoom in. I want to look at the hardware itself. Because this ZCU, it sounds great on paper. It aggregates I/O, simple. But when you actually try to build one, it sounds like a complete nightmare. You're stuffing so much functionality into one tiny box.
Let's open section 2 of the report then. Node strategy A, the zone controller.
The physical hub.
This is where the rubber meets the road, or maybe where the electron meets the silicon. The hardware challenge here is density, pure density. We're seeing this convergence of power distribution and data processing in a single enclosure.
And the car isn't getting any bigger. In fact, with the battery pack taking up the whole floor, packaging space is tighter than it has ever been.
Correct. The constraints are rigid, but the power density is just skyrocketing. Murata provided some data on component counts that honestly shocked me.
I saw that. They were talking about MLCCS, multi-layer ceramic capacitors.
The bread and butter of electronics, yeah.
Right.
A high-end battery electric vehicle, a BEV, with level 3 autonomy now requires approximately 30,000 MLCCs.
30,000 in one single car.
It's mind-boggling. And a huge chunk of those have to fit onto the circuit boards inside these little zone controllers.
So if you're using the standard capacitors used 5 years ago, you literally run out of board space. You'd need a motherboard the size of a pizza box.
Which drives the first major technical trend Murata highlights.
Yeah.
Miniaturization. We are seeing a hard shift in the industry standards. The IRFA 402 size, which was the standard small capacitor for a long time, is being replaced by these 0201 size.
Okay, for those of us who don't spend our days staring at PCBs under a microscope, give us a sense of scale. What is in 0201?
And 0201 is 0.6 millimeters by 0.3 millimeters.
It's dust. It's engineered dust.
It's basically dust. If you sneeze near the production line, you lose $100 worth of inventory.
Yeah.
But size isn't the only issue. It's the physics of the electricity itself. We're dealing with modern system-on-chips, SoCs, built on 5-nanometer or 7-nanometer processes.
These are the same class of chips you'd find in a high-end smartphone or a laptop.
Exactly. And these chips have a very specific and very difficult power profile. As the transistors get smaller and smaller, the operating voltage drops. These chips run at less than 0.9 volts.
Which sounds really efficient.
It is efficient, but it also makes them incredibly sensitive. Because to do the work, since the voltage is so low, the current has to be massive. We're talking about sudden current spikes of 100 amps or more when the chip wakes up to process, say, a camera image.
And there's the problem. If you have a sudden demand for 100 amps and your voltage is only 0.9 volts, even a tiny bit of resistance or inductance in the line causes a voltage drop, a sag.
Exactly. Ohm's law comes for us all. The voltage tolerance on these things is tightened to plus or minus 30 millivolts.
30 millivolts, that's nothing, that's noise.
It's razor thin. If the power dips even a fraction below that window, the processor crashes. The car's brain just resets.
So how do we prevent that? You can't just add more standard capacitors if you don't have the space.
You have to change the architecture of the capacitor itself. This is where the low ESL strategy comes in. ESL stands for equivalent series inductance.
I like the water pipe analogy for this. Inductance is like the inertia of the water in the pipe. If you turn the tap on full blast, the water doesn't come out instantly at full pressure. It takes a split second to get moving.
That's a perfect analogy. And in that split second, while the current is trying to get moving, the pressure or the voltage in the pipe drops. If it drops too much, the chip dies. Standard capacitors have too much inertia. They're too slow to respond to a 5-nanometer chip screaming for power.
So what's the fix?
Murata highlights two key technologies here. First is the LW reverse capacitor.
This one is visually interesting. If you imagine a standard rectangular capacitor, the metal terminals are usually on the short ends, right? Like a D-cell battery.
Correct. In an LW reverse, they flip it. The terminals are on the long sides.
Why does that matter?
It widens the road. By making the terminals wider and the distance between them shorter, you dramatically reduce the resistance and the inductance. The current can flow in and out much, much faster.
It's such a simple geometric hack, but it solves a really complex physics problem.
It's basic physics applied elegantly. And the second solution is the 3-terminal capacitor.
Adding a third leg.
Right. By adding a third terminal specifically for grounding, they significantly reduce the impedance, especially in high frequencies. This lets engineers use fewer capacitors overall.
Oh, okay.
So instead of needing, say, 10 standard caps to hold the voltage steady, maybe you only need 2 or 3 of these 3-terminal caps.
So you save space and you get better performance.
Exactly. So strategy note number 1 for our engineers listening. Stop using generic caps for the main processor power rails. It is a false economy. You need low ESL, period.
Got it. Now, let's talk about the other side of the ZCU. We've talked about the brain. Let's talk about the brawn. The ZCU has to actually drive things. Motors, heated seats, pumps. That means high current.
And high current means heat.
And heat is the silent killer of electronics.
It is. And we are talking about operating environments, especially if the ZCU is under the hood or near a battery pack. That can reach 150 degrees Celsius.
150 C, that's roasting. That's oven territory.
It is. Now, standard inductors, the coils used to manage that power flow, are usually made with a ferrite core. Ferrite is a ceramic material. It's cheap. It works well at room temperature, but it has a fatal flaw.
The Curie temperature.
Not even that high, just high operating heat. At these high temperatures, the magnetic properties of ferrite, they just degrade, the material saturates.
Meaning it can't hold any more magnetic field. It's full.
Right. And when an inductor saturates, it stops acting like an inductor, which smooths power, and it starts acting like just a wire with resistance. It stops filtering. The current spikes. And crucially, it generates even more heat.
So it gets hot, which makes it saturate, which makes it generate more heat.
It's a thermal runaway loop.
Yeah.
The strategic shift here, as outlined by Murata, is moving to metal alloy power inductors, specifically their DFE series.
Metal alloy. It just sounds tougher.
It is. Instead of a ceramic grid, it's a molded metal powder. The material physics are completely different. It has a much, much higher saturation current. It doesn't give up when the magnetic field gets strong.
And the heat handling.
Stable up to 150 C. It just doesn't degrade. So if you were designing a ZCU for a global platform one that has to work in a traffic jam in Dubai in July, you cannot rely on ferrite for the main power rails. You just can't. You have to specify metal alloy.
Okay, so we've armored the zone controller. It's got miniature, high-speed capacitors for the brain and heat-resistant metal inductors for the body. Let's move to the other critical node in this network. Section 3, the TCU.
The telematics control unit.
We used to just call this the modem, but calling it a modem today feels like calling an iPhone a calculator. It massively undersells it.
It's the gateway to the entire world. It's 5G, it's V2X vehicle to everything GNSS for satellite navigation, Wi-Fi, Bluetooth. It is the digital mouth and ears of the vehicle.
And for a software-defined vehicle, if the TCU goes down, the car is effectively lobotomized.
Completely.
It can't get updates, it can't see traffic, it can't communicate.
Correct. And the challenge here is maintaining that connectivity in a really hostile environment. And we have a specific problem that Murata calls the tunnel problem.
Oh, I love this example because everyone, literally every single person driving has experienced this. You're driving, you're using Google Maps or Waze, you go into a tunnel and your little arrow on the screen just freezes.
Or it starts drifting sideways into the river. Exactly.
Now, in a standard car driven by a human, that's just annoying. You glance at the road signs. But imagine you are in a level 3 autonomous vehicle. The car is driving itself. It enters a tunnel. The satellite signal vanishes.
If the car thinks it's still on the highway, but it's actually drifted onto an off-ramp, people die.
Exactly. This is unacceptable. So how do we solve the tunnel problem?
We can't make the satellites see through mountains.
We cannot. So the TCU has to switch modes. It has to move from absolute positioning using satellites to dead reckoning.
Dead reckoning. It sounds like something from a pirate ship.
It's an old nautical term, but the technology is cutting edge. It means calculating your current position based solely on where you were a second ago and how you've moved since then.
So I was at point A. I moved 50 meters north at 60 kilometers per hour. Therefore, I am now at point B.
Simple in theory, extremely hard in practice. Because to know exactly how you move, you need incredible precision. You need a 6 degrees of freedom inertial measurement unit, or IMU.
And Murata references their SCH-116T sensor here. Right. So 6 degrees of freedom means it measures acceleration in 3 directions.
Yeah.
Up, down, left, right, forward, back. And it measures rotation in 3 directions. Pitch, roll, and yaw.
So it feels every single bump, every curve, every lane change.
And it takes that data, combines it with the wheel speed data from the car, you know, how many times the tires have turned, and it integrates that math to draw a line on the map.
But the problem with integration is drift, right? If your sensor is off by even a tiny, tiny fraction of a percent, that error multiplies every single second. After a minute in a long tunnel, you could be 100 meters off.
Which is why the quality of the silicon is so critical. The bias stability of the gyroscope has to be near perfect. This is not the accelerometer in your Fitbit that's guessing if you walked a step. This is safety-critical hardware.
And it has to diagnose itself.
That's the other key point. The Murata SCH-16T has over 200 internal monitoring signals. It is constantly checking itself. Is my memory working? Is my voltage stable? Is my sensing element broken?
Because the worst thing isn't a broken sensor. The worst thing is a sensor that lies.
Precisely.
If the sensor tells the car, we're going straight, when you're actually in a turn, that is a disaster.
It is. It's much better to shut down and hand control back to the driver than to provide false data. That is how you meet the ASIL-D safety standards.
Now, physically, where does this TCU live?
To get the best signal, you want it high up. Usually on the roof, often integrated under that shark fin antenna you see on most modern cars.
Which is a terrible place for electronics.
The absolute worst. It is essentially a greenhouse. The sun just beats down on that black plastic fin all day. Temperatures can soar, and because it's on the roof, it's subjected to constant vibration from wind and road noise.
So how do you keep the chips inside from just vibrating off the board or crack in the solder joints.
The solution is resin molding. Murata discusses this for their communication modules. Instead of just having a circuit board inside a plastic box with air inside, they actually encase the entire set of components in a high-grade resin.
So it's like a solid brick of electronics. Effectively, yes. They pot the electronics. This resin does two things. First, it acts as a vibration damper. The components literally can't shake loose because they're solidified in place.
Right.
It prevents those fatigue cracks in the solder.
And the heat.
The resin is thermally conductive, so it pulls the heat away from the chips and dissipates it to the outside casing. It basically acts like a distributed heat sink. This allows these modules to survive the Automotive Grade 2 standard, which is -40 Celsius, all the way up to +105 C.
It's amazing how much of this high-tech digital revolution just comes down to material science. Resin, metal alloys, ceramic geometry.
Strategy is very often about materials. You cannot code your way out of a melted chip.
That is a quote for the wall right there. You cannot code your way out of a melted chip.
I might have to put that on my business card.
Okay, let's move to section 4. We've built the body, which is the ZCU. We've built the senses, the TCU. Now we need to talk about the blood flow, the power architecture. And for this, we're turning to the intelligence from Renesas.
Right. Renesas gives us the view from the silicon brain itself. We've established that the central compute, the HPC, is getting more and more powerful. We're talking about their ARC-card Gen 5 SoCs. These are supercomputer-level chips.
And supercomputers are hungry. And they are very picky eaters.
They are. The old way of doing things was to have one giant power management IC, a PMIC, that tried to handle everything. It was like a main breaker box for the whole chip.
But Renesas argues that for these new complex architectures, a single PMIC just creates a bottleneck.
It becomes a thermal hotspot. If you're trying to push 200 watts through one single chip, it gets incredibly hot. And routing all the power traces on the board becomes a nightmare. You have to run these thick copper lines all over the PCB to get power to the different parts of the SoC.
So what's the strategic shift?
A distributed power architecture. They call it the system PMIC plus sub-PMIC approach.
Break that down for me.
Okay, think of it like the power grid of a city. You have a main power plant. That's your car battery. Then you have a regional substation that handles the high voltage distribution. That's your system PMIC. It handles the logic, the communication, the safety checks.
Okay, I'm with you.
But then, right next to the neighborhood that actually needs the power, you put a local transformer on the pole. That's the sub-PMIC. You place these smaller, dedicated power chips right next to the specific parts of the processor they're powering.
So if the GPU part of the chip needs 50 amps to render a 3D map, you put a sub-PMIC millimeters away from the GPU power pin.
Exactly. This reduces the distance the high current has to travel. Shorter distance means less resistance, less heat, and a much faster response time.
But the real killer app feature here, according to their report, is the sequencing.
Ah, yes. Sequencing. This is something people often forget. A complex system on chip doesn't just turn on like a light bulb.
It has a wake-up ritual.
It has a very precise wake-up ritual. It has to power up in a very specific order. Core voltage on, wait 5 milliseconds. Memory voltage on, wait 2 milliseconds. I/O interface on. If you get the order wrong or the timing wrong, you get what's called latch up.
And the chip either freezes or it fries itself.
Correct. In the old days, you'd set this timing by soldering specific resistors and capacitors onto the board. It was hard-coded in hardware. If you changed the chip in the next generation, you had to redesign the entire board.
Which is slow and incredibly expensive.
The Renesas system allows this sequencing to be programmable via a GUI. It's digital. You just plug in a laptop and say, change delay from 2 milliseconds to 5 milliseconds, and it's done.
That's a huge deal for flexibility. It de-risks the entire hardware design process.
And it optimizes the bill of materials, the BOCM. Renesas data suggests this approach can reduce the component count by 40 to 50% compared to using discrete power components.
40 to 50%. That's half the parts. That's a lot of money and a lot of reliability points right there. Now, we also need to talk about 48 volt. The Renesas report mentions this trend, driven largely by Tesla and the Chinese OEMs.
48V is the logical solution to the high current problem. It goes back to basic physics. Power equals voltage times current. P equals VI.
The classic equation.
So if you need more power because your windows are heavier, your seats heat up faster, your computer works harder, you have two choices. You either increase the current or you increase the voltage.
If you increase the current, you need thicker wire, and thicker wires mean heavy, expensive copper.
Exactly. So the industry is moving to 48V. You quadruple the voltage from 12V, which means for the exact same amount of power, you only need 1/4 of the current. You can use much thinner, lighter wires.
But you can't just plug a standard 12V chip into a 48V battery. It would explode instantly.
Instantly. Correct. So the ZCU and the central compute need very sophisticated pre-regulators. These are chips that take the raw, noisy 48V from the battery and step it down to a clean 12V or 5V. Renesas really emphasizes the need for 48V to 12V buck converters that are highly efficient.
Because if they're not efficient, that voltage drop just creates heat.
Waste heat. And we don't want space heaters on our circuit boards.
Speaking of power distribution, there's one more really cool piece of tech in the Renesas report. Smart fusing. The E-fuse.
This is the end of the melting wire. A traditional fuse is, it's ancient tech. It's a piece of metal designed to melt if the current gets too high. It's simple, but it's dumb. And once it blows, it's gone. You have to physically replace it.
Which is a massive pain if your zone controller is buried deep inside the door panel or under the dashboard. You have to take the car to the dealer just to replace a 50-cent fuse.
Exactly. An E-fuse, or a smart power stage, is a silicon switch. It monitors the current digitally. If there's a spike, it cuts the power in microseconds, which is much, much faster than a melting fuse.
But the best part is that it's resettable.
Right. If the spike was just a temporary glitch, maybe you drove through a puddle and a sensor shorted for a millisecond, the software can wait, check the line, and say, okay, that looks clear. Let's try turning it back on.
And it provides diagnostics.
It tells the central brain why it tripped. I saw a short circuit to ground on the left window motor. That makes servicing the vehicle infinitely easier. The car can effectively write its own repair ticket.
It really is a nervous system. It feels pain and it reports it, rather than just dying.
That is an excellent analogy, yes.
Okay, let's move to Section 5. We've built the hardware. Now we need to talk about the conscience of the car, functional safety.
ISO 26262, the standard that keeps automotive engineers up at night.
For the uninitiated, this is the automotive standard that ensures that when electronics fail, and they will eventually fail, they fail safely. They don't cause the car to, accelerate uncontrollably or turn off the headlights at midnight on a dark road.
Correct. And in this report, we see two different approaches to safety, the active and the passive.
Let's start with active. That's the Renesas side of the house.
Renesas approaches safety through active monitoring. Their PMICs and system chips have built-in watchdogs.
A watchdog timer.
It's a circuit that is constantly tapping the main processor on the shoulder. It's asking, are you still there? Are you still calculating correctly? And the processor has to constantly reply, yes, I'm here, I'm fine.
And if the processor doesn't answer, because maybe it's frozen in a software loop?
The watchdog bites. It resets the system or forces it into a limp home safe mode. They also monitor voltages. If that 0.9V line creeps up to 1.0V, that's an overvoltage event. It cuts the power before the processor can fry itself. This is how they achieve ASIL B to ASIL D ratings.
And they mentioned this term COC, safety element, out of context. That sounds like legal jargon.
It is, but it's very useful jargon. It means they design the chip to be provably safe, regardless of where you use it. They provide all the documentation, the SASE manuals, the failure rate analysis, so that the car manufacturer can just slot it into their system and prove to the regulators that the whole car is safe.
It saves the car maker a massive amount of paperwork.
Years of paperwork.
Okay, that's active safety. Chips watching other chips. Now, what is passive safety? How can a capacitor or a crystal be safe? It's just a rock or a piece of ceramic.
Murata's approach is all about precision and reliability. Take the timing device, the crystal oscillator. This provides the heartbeat for all the digital signals.
Like the drummer in the band, everyone plays to the beat of the crystal.
A perfect analogy. But in a modern car, you have high-speed Ethernet and Wi-Fi. If that drummer is even slightly offbeat, if the frequency drifts, the data packets collide. The network crashes.
And why would it drift?
Heat. It's always heat. As crystals get hot, their frequency changes. So Murata emphasizes crystals with a frequency tolerance of just plus or minus 10 ppm parts per million.
That is incredibly tight.
It is essential. If your timing drifts because the ZCU got hot, your autonomous drive system could lose sync with the cameras, and the car goes blind. That is a safety failure. So a passive component's quality is a safety feature.
They also mentioned thermistors, which are basically just temperature sensors.
Yes, NTC thermistors. But again, it's not just about slapping a sensor on the board. Murata talks about using simulation tools, RT simulation, to model exactly how the resistance of that thermistor changes with temperature.
So the ZCU can actually predict a hot spot before it happens.
It could detect a subtle temperature rise before it becomes critical. It allows the system to throttle back performance, maybe dim the screens or slow down the battery charging to cool down. That is proactive safety.
And the goal for all of this, as stated in the documents, is 0 defects.
0 ppm failure rate. When you're building 1.72 billion units, even a 0.1% failure rate is millions of broken cars on the road. The supply chain management and the testing required to even attempt to hit 0 defects is a strategic capability in and of itself.
Okay, expert, we have covered a massive amount of ground. We've gone from the 30,000-foot strategic view all the way down to the 0.6 millimeter capacitor. Now, I want you to put your consultant hat firmly back on. We need to synthesize this.
Let's proceed to Section 6. Implementation Roadmap and Strategic Advice.
Imagine I'm the chief engineer. I've just listened to this entire briefing. My head is spinning with acronyms. What do I do tomorrow? What are my marching orders for my team?
Based on the synthesis of the Renesas and Murata intelligence, here are your 4 strategic imperatives.
Okay, hit me. Number 1.
Strategy 1. Power integrity first. You must stop treating capacitors as an afterthought or a commodity. If you are using 5-nanometer or 7-nanometer CXCs, you must prioritize low ESL and 3-terminal capacitors immediately.
So tell my procurement team to stop buying the cheapest caps on the market.
You tell them if they save pennies on caps today, you will spend millions of dollars debugging processor crashes tomorrow. The total cost of ownership overwhelmingly favors the advanced capacitor.
Got it. Okay. Number 2.
Strategy 2. Material change for zonal hubs. For your zone controllers, you must mandate a switch to metal alloy inductors. The thermal profile of a ZCU, that combination of high current plus high ambient heat, is a death sentence for traditional ferrite. Update your approved vendor list, your AVL, to require metal alloy tech like the DFE series.
Clear. Ferrite is out, metal alloy is in. Number 3.
Strategy 3. Redundancy by design. You have to stop trying to power your central brain with one single giant chip. Adopt a system plus sub-PMIC distributed power architecture. It gives you thermal spreading, better transient response, and the redundancy you need to achieve ASIL-D safety.
Divide and conquer the power. And the last one.
Strategy 4. Digital verification. You cannot prototype your way to perfection anymore. It is too slow and too expensive. You must use the supplier tools, Murata's sim surfing for EMI filters, Renesas CAR tool for functional safety analysis, early in the design phase.
So simulate the heat, simulate the noise, simulate the failures before you ever cut a single PCB.
Simulate before you solder. It's the only way you're going to meet the 2027 timelines.
This has been intense, but I feel like we've actually built a real roadmap here. We aren't just hoping the software works, we're building the physical foundation for it.
We have connected the physical reality of the hardware to the strategic goals of the software-defined future.
And that, I think, brings us to our final thought.
If there's one thing I want the listener to take away from this whole report, it's that connection. We talk endlessly about the software-defined vehicle. We talk about the soul of the car being the code. But the soul needs a body. And if the physical layer, the capacitors, the inductors, the power chips, isn't robust enough to handle the heat, the power spikes, and the signal noise, the software cannot function.
The code is only as good as the silicon and the ceramic it runs on.
Exactly. The winning combination, to borrow a term from Renesas, isn't just about picking a good processor. It is the co-design of active silicon and advanced passives. You need the brain and the nervous system working in perfect concert.
It's an entire ecosystem. And for the engineers listening, you are the architects of that ecosystem. You are building the machine that makes the code possible.
It's a heavy responsibility, but I think it's an exciting one.
Thank you, expert speaker, for this briefing. That was a masterclass.
My pleasure. A real pleasure to analyze.
And to you, the listener, the chief engineer, good luck. The 2030 deadline is approaching fast. You have your report now. Go build it.